Good evening and welcome from the woods of Maine. Uh, this is another episode of Talk on the Rocks, and this is going to be dealing with 1.2 billion year history of the New England region, more or less the emphasis on the New England region, in particular Maine, New Hampshire, Vermont, and some of southern New England. Um, and I'm going to incorporate and use the marginal way of Ogunquit, Maine, my hometown where I'm from, to display and use examples of how the events of the Appalachian Mountains unfolded. Uh, the rocks on the marginal way are classic Iapetus Ocean sediments. The Iapetus Ocean was an ocean that was essentially occupied the Atlantic before the Atlantic was there. However, it was not in the same location. It was just an ocean off the east coast of the United States. And this ocean opened up about, between 7 and 530 million years ago, when, believe it or not, the west coast of Argentina separated from the east coast of the United States. And oddly enough, you can imagine the west coast of South America, Argentina was actually it was right offshore here. And if I'm not mistaken, the continent was actually spun upside down from its orientation right now. So 600 million years ago, that separated. An ocean opened up. And then, after about 200 million years, it began to close. And as it began to close, a series of island arcs got smashed and accreted onto the east coast of North America, starting with the Taconic Mountains of Vermont, and then the Gandaria area, which occupies more or less the majority of central Maine and central Mass, part of central Connecticut, and what have you. Not really anywhere in Rhode Island, and that is Gandaria goes also up into Nova Scotia, and it's basically a series of arcs and crust that got crunched from the Iapetus Ocean. Not a true microcontinent, but more or less a melange of it. And that got smashed into Maine and New Hampshire and Vermont. And as it did, it essentially squashed about 1,000 miles of ocean into about 100 miles, 150 miles. Most of it was subducted, but there's a good amount that's been metamorphosed in the central New England area. And then when that finally closed, that announced the arrival of Africa, Pangaea, off the coast here, and it built a gigantic mountain range. And then in the Triassic period, about 170 million years, a little bit later. I'm sorry. In the Triassic period, the early Triassic, about 240 million years ago, the continents of Europe, Africa, and the Americas began to separate and open up the Atlantic Ocean, which is what we see today. And this is recorded very well in these rocks in this little area where I'm from, Ogunquit, Maine, on the Marginal Way. So, here we go. So, as I said previously, I am from Ogunquit, Maine. This is just a global map, give you an idea of where I'm at. Here's Maine, here's the Marginal Way, and Ogunquit's right in there. I wish I could blow that up, but I can't. So you just have to take my word for it. A little closer to home, I'm located here in southern Maine. Actually, we call it southwestern Maine. It's sort of odd to call it that, but that's what it is, in the Marginal Way right here. And if you look, you can see vaguely some different, really it's to the trained eye, but this terrain right here is different from this terrain right here. which is different from this terrain right here, which is different from this terrain right here. And all of these are recording the impacts and the additional land or real estate, if you have, as the Iapetus Ocean closed. Most of the Iapetus Ocean is really right in here, and it goes down over here. And then you have the coastal volcanic island arc, part of Avalonia, which is a microcontinent, which we'll be talking about. You have an island arc right here, and then right next to it, you sort of have what I would probably consider it more or less a trough or an area of deposition that creates this line of mountains right here. These are the Longfellow Mountains of Maine. They go all the way up to Mount Katahdin, which is right here, this bald spot, and then down here to Mount Washington, which is this bald spot. And then, of course, you've got some mountains here and here, but these are all compacted silts of the Littleton Formation, and it is thought that a lot of these came from actually the east, not the west. Some did come from the west originally, but then more came from the east, and they piled up into this trough right here, and welded and metamorphosed into a very hard rock because there's plutonic activity all around this, and cooked these rocks. So they make up the resistant backbone of Maine and New Hampshire. The Vermont mountains are older. They are associated with a different mountain building episode called the Taconic orogeny, which happens earlier, around 500 or 480 million years. So 480 here, about 400 here, maybe 360, a little less over here. So basically, the further you go southeast, the younger, well, not the younger, the younger, it gets younger as you basically go from northwest to southeast until you hit Avalonia, which is a much older piece of Africa. But that's for later. So the gist is Adirondacks here are part of the Grenville orogeny. They're 1 billion years old. This is about 500. Again, this is about 4, and then these are in the upper high 3s into 300 million years, and then everything got smashed, and that was the end of that around 300 million years ago in the Carboniferous. Close-up of the Marginal Way. I guess it's not really close-up, but it just shows the town. This is the beach I'm from, the river, my little town I grew up, probably right there. Interesting that you can see these. I've never. How was that? All right. I've never noticed these right here, but these are sort of weird bog depressions. I don't know exactly what those are caused from, but they seem to be linear, and I don't know why. In any case, they're probably following the rock formations have a tendency to go like this, so they're probably just following subsurface bedrock. This is a map composed of by Dr. Hussey, Dr. Arthur Hussey II, to be really specific. He's a wonderful man. He passed away a few years ago. He is the man of geology in this area. You look on any map, almost all publications having to do with the real guts of geology, the petrology, the hard stuff, stuff that describes everything you need to see. Dr. Hussey is the guy that did this. And this is one of his original maps back in the day, and he sort of fell in love with Ogunquit when he was a young guy, and rightfully so. It's a beautiful place. After he passed away, he essentially bequeathed this tour that he used to do to me, and then I do it. And as you can see, it's complex geology, mostly quartzites, but there's phyllites, and you're just layers upon layers. And I guarantee you that if I went in to do this map again, or anybody did this, they're going to get slightly different results than what he got. We've learned a lot in the time since he did this. I'm not taking anything away from him, but it is our jobs as geologists to prove we take the ideas of our forefathers and we act on them, and we try to prove them wrong, and we keep trying to prove them wrong or reinterpret them until we can just basically concede that it cannot be done and that person was right. So this is this is very generalized. Granted, it's showing a lot of igneous dikes that signify the opening of the Atlantic Ocean. The rock that it was intruded in, these are all layers of sediments that were laid down in the Iapetus Ocean, fairly close to shore. We think that the actual source was offshore, not from. Sediments have more of a African signal, and by signal I mean we use zircons to look and get um, a geochemical reference of where these sand grains came from that made up this formation. And as it turns out, they are very old and older than geochemist. Yeah, I can't say that word. Geochemically, unlike Laurentian, which Laurentian is a name for North America prior to the Pangaea. Um, Prior to Pangaea, and these sediments do not have the signature of North America. They have the signature of someplace in Africa, which means that they came from a source east of where we presently are, where the ocean is. So at one point, you'd look outside and you'd look east and you'd see a giant mountain range coming towards you, kind of like Japan. So, in order for this talk, I think it's important to emphasize the fact that this is a fairly in-depth talk. This is, for a person that's not educated in geology, this is more geology than they could ever want. It may even trigger some wanting to learn more, but this is definitely right up there around graduate level stuff. However, I love explaining complex situations to make them simple. So I'll do my best because we all start somewhere. And so what the objectives are, we're going to cover the geologic history of 1.2 billion years. And I use that because we're basically going to close the Atlantic Ocean. This is essentially going back in time. I'm going to bring Africa back, and then I'm going to send it away and create the Iapetus Ocean. And then I'm going to bring Amazonia, I'm going to bring South America up, rotate it, and then slam it back into us about 1 billion years ago when the supercontinent of Rodinia existed. There's been about 5 or 6 supercontinents. Rodinia is the one that was existed prior to Pangaea about 300 million years ago. Rodinia came together about 1 billion years ago, a little earlier, and broke up about 700 million years ago. And that is where our story kind of begins. Because prior to 1.2 billion years, our coastline was somewhere in New York, somewhere west of the St. Lawrence River, probably somewhere in Ohio, Tennessee. You make that line trending northeast, southwest. That was where our coastline was. There were no Appalachians. They did not come until about 400 million years ago to 300 million years ago. And the mountain range that was there were called the Grenville. It was a Grenville orogeny, and it was gigantic. When it came together, it rivaled this, maybe even it was bigger than the Himalayas. It is the most major continent-continent collision that I can think of on North America on the East Coast, besides the actual impact of Pangaea. So, because Pangaea also made a Himalayan-sized mountain range of the Appalachians. So, I'm going to go over some topics and definitions used, review of the formation of the planet, the creation of North America. I need to build it in order to modify it. And again, Laurentian is North America. It's just prior to anything before about 300 million years is you refer to as Laurentian. It's not North America because it has bits and pieces of other things attached to it. We're going to go over geologic time, Wilson cycles, large igneous provinces, ellipse, the supercontinent of Rodinia, which I've touched upon, Pangaea, the Iapetus Ocean, and the Atlantic Ocean. Those are all really important in this discussion. And then I'm going to use modern analogies around the world, or planet rather, to show you what I think the environment may have looked like locally at the time. As they say, a picture's worth 1,000 words. So, and I talk too much as it is. We're going to emphasize some of this geologic action in southern Maine, and we're going to use references to Mount Washington, Katahdin, and rock formations of the Marginal Way. Between those, triangulating those three things, we can get a really good idea of what happened. Time will be focused on North America through 2 supercontinent Wilson cycles, including the Grenville orogeny, the construction of the supercontinent Rodinia, the breakup of Rodinia, and the opening of the Iapetus Ocean. Then the closing of the Iapetus Ocean. That includes at least 3 at least. I mean, it's very, but the tectonic the Acadian, and then the Alleghanian. And then Taconic is Vermont, Acadian is Maine, New Hampshire, part of Mass and Connecticut, and then the Acadian is the arrival of Africa. And that forms Pangaea. At the end of once Pangaea comes together, it has dire consequences on the planet. And Rodinia may have what has well have too, but life was not that far advanced yet. So the extinction event is not as obvious. But anyways, at 252 million years, we have the largest extinction that ever occurred, and that is known as the Permian extinction event. Then we're going to break up Pangaea, open up the Atlantic, send Africa on our way, and then we're going to talk a little bit about the Mesozoic period, the KT extinction, the Cenozoic period, the Pleistocene Ice Age, and then the future of the North American coast. And the reality is you don't see any rocks in New England. It's with the exception of igneous volcanic edifices in New Hampshire and Maine, and in the opening of the Rift Valley of Connecticut. There really isn't anything younger than about 360 million years old. So you have a gap in time for 360 till about to really about 170 million years. And the reason why is not that nothing was here. It's just gone. It's eroded. It's offshore. And what we see now are the exposed roots of the internal structure, the guts of the Appalachian Mountains, which is why there's so much granite and hard rock. All right, geologic time. This is supposed to be a circle. It is. I stretched it, so now it's a donut, and it looks sort of ridiculous. But so this is geologic time as a donut, and geologic time is very long. It is uncomprehendibly long to people that don't understand it. It's even the same way for people that do, like myself. I keep myself awake at night thinking about time because it's unbelievable. But anyways, 4.5 billion years. We'll just 4.54, 4.56, whatever. 4.6. This is when our Earth kind of coalesced. It came together. You got the moon at 4.57. Earth came together at 4.56. So really the moon was right on the heels of the formation of the Earth. And the moon is an interesting topic in itself. And around 4 billion years ago, and this period is called the Hadean, by the way, there really isn't any life in this time. It's just a molten sea of lava and magma churning. Maybe there's some pieces of crust beginning to form, not much. It's just convection is too much. Earth is just too hot and too young. Around 400 million years ago, maybe a little earlier, into about 3.8 billion. And actually we use that term as the border of the Hadean. We have what we call the late heavy bombardment, and we know that from the moon. And that was, we believe, triggered by the moving of Jupiter through the solar system. We think it either migrated out, we think it formed closer than migrated out, and we think actually the ice giants, Uranus and Neptune, formed between there, Jupiter and Saturn, and when they shifted gears and moved around, it basically caused a bunch of problems. And even though that our solar nebula had balanced a little bit, well, it wasn't enough, and so everything kind of went haywire for about 300 or 400 million years, and it just basically whacked everything. So there's craters all over the solar system from this period of time. 3.8 billion years, we go into the Archean period, and then photosynthesis starts. It starts converting. 3.6 billion, maybe 3.5. And this is when you have very simple cell organisms that are able to take sunlight and begin to photosynthesize and create energy out of that. And that is a big step for us. This is the step. This changes us. This makes our first cells. And really, we continue for half of Earth history almost, basically doing that and pumping out CO2. Pumping out oxygen, because these things breathe oxygen, breathe carbon dioxide, produced photosynthesis, and then release oxygen. And so over time, over a couple billion years, oxygen begins to stack up. And as the oxygen does start up, well, it comes at the expense of CO2, which is a greenhouse gas, which guess what? You start taking away carbon dioxide and you put oxygen in the air. You also start creating ozone, so you have protection from the sun's rays, but you do start cooling the climate. And so the Archean ends at about 2.5, and this is just an arbitrary number. I mean, there's a couple things that happen, but time this far, you just kind of pick your numbers. Then around 2.4, 2.3 billion years ago, we start to see oxygen really starting to come into effect. We start to see changes in minerals that have oxygen, and rust. Rust starts to show up right around here. So we know that up until this point, almost half the time, there wasn't much oxygen. We didn't, and iron did not rust. It's right about this time, about 3,000 or 4,000 new minerals show up, and they all have, a lot of them have to do with oxygen. So we know that there was an oxygenating event right here. And then we went into a major glaciation, and we almost got snuffed out. This is what we refer to as snowball Earth, about 2.3 billion years. And it literally may have frozen. It may have just been one giant snowball. Maybe we're talking ice at the equators over the ocean. And it lasted a very long time, hundreds of millions of years. And so this period of time here is the Proterozoic. And the Proterozoic is a monster. It is the biggest geologic period. It's almost half of time. And a lot happens in the Earth. Essentially, the way I look at it, this was the part of the Earth that is just completely foreign, but now you start here at 2.5 billion years, and by the time we end up at 542 million, we have created an Earth that is starting to look kind of like us. And it all happens right here in the Proterozoic. So this is a 2 billion year time period. And if you notice, right around 2.2, we start to get single cell organisms going into multi-cell organisms called eukaryotes. So these are prokaryotes. We go to eukaryotes. And then the eukaryotes begin to start to stack. And that creates multicellular life. Like at first, the birds of a feather flock together. You just have the same cells kind of making mats, i.e. the stromatolites. So it's been around for a very long time. And then they start to actually, the stacking cells begin to start to have purpose. And maybe one cell, one place does something better than it does in another. And they start to take individual characteristics. And that leads into multicellular life. And then on the Ediacaran, or close to the Ediacaran, it's the late Proterozoic, we begin to get what we would consider the first animals, things that may have moved, things that basically result and this is all in the oceans. Nothing has happened, and anything in this period here is not using really. This is in the ocean. It's very simple. It may have not even really used sunlight. We think that the Ediacaran life forms were deep. They may have survived off sulfur or some other form of energy. But when you get right around 540 million years, this is when things happen. This is when life explodes, and almost all animal groups are now present that we see here evolved into what we see today. So your arthropods and the basic building blocks for your animals starts here, and then they start to really diversify. Why we go from this simple stage also into a blooming of life is still under a lot of debate, because we have some animals, we have some things are going, and then there's an extinction event. There's a couple snowball Earths. So life is trying to get going, but it keeps getting snuffed until right here, and then things just go ballistic. And I don't have an actual single cause as to why that happened. We think it has something to do with coming out of the ice ages, and we think that the passive margins allowed time to really, it gave life a chance to really start to evolve. When you're on active margins, there's volcanoes and everything blowing up and earthquakes, you don't live very long. But on the passive margins, and this is when we first start seeing passive margins right around here, and these are the margins created by Rodinia when it broke up. So Paleozoic, this means this is the life. This is prior to life. This is life. This is prior to life. Proterozoic. And Paleozoic is simple life, or what we think would be simple, but it's not. Everything starts simple and it gets very complex for the next two to 300 million years, only to get whacked at the Permian extinction event at 251 million years ago. Um, in this time period, you give rise to your arthropods, you give rise to your insects, you give rise to your amphibians. Your actually goes worms, lungfish, fish, amphibians, reptiles, mammals. That is the sequence. And each one of those would not exist without the other. Yeah, an amphibian worked great because everything was in the water up to a point, and then land animals started to come around. Well, guess what? That slime does not work so well when you're in a desert. So the reptile just basically evolved from the amphibian so that it didn't need a wet skin all the time. That's the only difference. And then we are a form of reptile that evolved so that we can actually keep our blood warm as opposed to having to use the sunlight. So we're all taking what existed and then adding another trait to it, and that's evolution. Um, and after the major Permian extinction event, what does make it through, and believe me, it's not much. Um, Everything rapidly diversifies. It starts slow, but then once it gets going, the reptiles just go ballistic, and we have rise to the dinosaurs in the Mesozoic. And the Mesozoic is the period of dinosaurs. And then, of course, they get their chance to, they get whacked at the end of the Mesozoic, 66 million years ago. And then the Cenozoic is the rise of us, the mammals. And if you notice, the humans don't even have a click on here. And if this was a 12-hour clock, dinosaurs are really showing up at like 11 at night. So we really, time is just unfathomably long. I mean, this is like maybe 10 o'clock, and this is the Paleozoic. I mean, this is almost 500 million years ago, and this is when really the first vertebrates came around. So you're looking at the reading 10 hours of just basically very simple. So the majority of the time it's either been nothing or single cell organisms. This is just another just another graph of the clock. You know, again, we're here. And there's just time is where our time has been on Earth has been very short compared to most others. Because of the clock and stuff doesn't really give you what I really want to emphasize how long time is, but this one really does it. So you start here, you go to here, you got your prokaryotes, 4 billion. Go through here. And you get to the Proterozoic. You get the Paleoproterozoic, you come up, you go like here, you come up here, and you're in the Archean. And you start to get photosynthesis. Then you come into the Proterozoic, and you go all the way around over here, and then you start to get eukaryotes, and then multicellular life, and then animals, and everything we know up here. And look at here's humans. It's like a pen mark. It's nothing. But this is how long time is. I mean, it is just ridiculous. That is a glaciation. That is a huge glaciation. What, 25 million years of ice? I mean, my God. This one was almost, the Sturgeon is 60 million years? I mean, my God. Can't even imagine, what that would be like. But anyway, that's just another time chart. And then there's this one. This is the granddaddy. It's got sea levels and oxygen isotopes and carbon isotopes and what the continents were and each time period. I mean, broken down, polar reversals, all of it. My only gripe is that they show the Precambrian and the Proterozoic over here as super small and making it look like that the rest of time is much larger when in fact it's the exact opposite. But if you really want to get an idea of what's going on in geologic time, this is a graph to look at. I obviously am not going to go through it because we'd be here forever. All right, planet formation, step one. So in order to understand how the Earth formed, you have to understand a few basic concepts, and the most important of that is being gravity and mass. And really, nothing happens without those two things. And we have tools to look at what has happened on Earth outside of the gravity and mass. I'm going to get to that in a minute. But for instance, I'll walk across. I'll walk or drive across New England, and it's pretty there's mountains in some areas, but it's pretty flat in others. And if you notice, you'll see slates and schists and rocks that seem to the trained eye get higher degrees in metamorphism, which means they are buried deeper and cooked higher. So there's brighter minerals, and then it will sort of reverse itself as you go to the other side. And basically, you're looking at the internal structure of a mountain, and the top of it's been all gone. So that's how we kind of figure out how things are occurring and events that have happened in the past. We look for the signs. It's like, it's the signs of the crime are all there. And that's why when we go to Mount Washington, we look at it, or Mount Katahdin, and they're two very different things. Washington is basically a gigantic pile of sediments like you'd find at the opening of the Mississippi River that have been completely compacted, cooked, compressed, smashed, and welded together to become very resistant, and they now form the high resistant peak that Mount Washington is on. But it's nothing more than river sediments a long time ago. And then Katahdin was buried. By the way, Mount Washington was also buried by about 6 miles of debris of Earth. But Katahdin is a gigantic volcanic edifice associated with the closing of the Iapetus Ocean, and it's a huge granitic intrusion, most likely a magma chamber. In fact, it was a magma chamber. We know that because off to the north, about 15 miles or so, there's the Traveler rhyolites that just so happen to match the granite of the Katahdin Pluton. So I mean, I am a scientist. I'm going to put my money that those two are very related. So the Katahdin area, the Katahdin volcano erupted all this rhyolite, which is a very felsic, explosive. Think of Mount St. Helens, but on a much bigger scale. Very explosive, piled up around the edifice, the area where it's erupting, and then over time it built a mountain, and then it actually injected its own materials. So that's why you have the granite inside the rhyolite. So yeah. So the Hadean, I kind of went over that a little earlier. The Hadean is when we essentially have the accretion of the planet. I'm not going to go into this huge details, but the gist of it is that, as I said, that mass and gravity have everything to do with how our Earth formed and our solar system. And the short version of it is that we had a star supernova somewhere in our vicinity of the galaxy, and it left a field of debris and atoms and gas and all sorts of matter. And for a good couple of billion years, it sort of existed as a big giant cloud, I guess you could say, a nebula. Well, somewhere, don't know really how, we don't know when, at least not, I've never heard anybody conclusively tell me this, but or the origin, but we know that a shock wave went through this nebula cloud, and it was just enough in some areas, or at least in one area, to get a couple of things to attract to each other, i.e. Hydrogen atoms. And those hydrogen atoms, all it took was a couple, and once you get a couple, you start to get more and more and more and more and more, and eventually they will start to fall in and gravitate towards each other, and there'll be a ball of hydrogen, and that ball of hydrogen is going to start sucking in more hydrogen and other gases, but mostly hydrogen. I mean, the sun is almost pretty much, the only thing is, I mean, there's trace elements of other stuff, but for the most part, it's a hydrogen gas ball that's converting hydrogen into helium. And in the Hadean time, the sun had accreted, it had ignited, it was smaller, it was less bright, but it was very young. And in that, the sun took up 99% of all the matter in its vicinity in the solar system. The other 1%, I think of that, 80% to 95 to 90% went to Jupiter. The other mass of that went to Saturn, and then you made the planets. And all of them have different histories, but yet they're all very similar. And they all came out of the same stuff, which is interesting because they all have the same stuff, but because there's certain distances away from the sun and the amount of of solar wind that blows when the sun ignited, it blew a bunch of stuff out. Um, uh, because of the size and the difference in the size and the mass of the planets, they all have formed into different different looking planets that we see today. So that's the Hadean. And in the Hadean, the Earth basically was a molten ball. It got whacked. The moon ended up forming from that. And basically it was a Mars-sized planet that hit us called Theia. Is it Thera? I forget. Well, it's something close to that. And when it did, it stripped off. It basically, we absorbed the core and the material from that planet, but it also blew a chunk of it off. But it blew off a lot of silicate material, the outer shell. So the moon, for its size, is actually lighter than it should be, and it contains more silica than it should in a smaller iron core, whereas the Earth has a larger iron core and less silica than it should. And the larger iron core gives us the magnetic field which protects us. So believe me, there's so many things that needed to come together for us to be here. So let's just be glad we're here. Archean eon. This is, the idea that we had the late heavy bombardment when Jupiter decided to make a shift. We have now. See, this is a very debated concept. When did plate tectonics really start? We are still trying to figure that out. I mean, there's people that, there's classic plate tectonics, and there's drips, there's lids, it's just so many different things. I've watched so many videos and read, it always changes. But the point is that sometime in the Archean period, whether it be subduction or dripping, and dripping is basically, you don't have plates sliding under each other, you have different densities where a plate will get heavy and then it will just snap and fall. Almost like there's a very thin layer of pasty crust, but it's not moving and not really banging into each other per se. It's just what it's doing is that there's more felsic, some felsic material, lighter material coalescing and coming together, and then the areas in between get thick and heavy, and then they fall, and then it drags these two pieces into each other. That would be a more likely scenario, and then you get something that looks like this. So take away the actual subduction and just have these sections in here drop. Now, this may exist. I don't know, but we seem to think it may have not, and for a variety of reasons which I'm not going to go into. But in any case, these as the crust began to cool, it began to separate iron. Iron is the first to come out of liquid lava, magma melts, molten melts, and the remaining material became more and more silica rich, and it became lighter, and therefore it began to float higher than the actual mafic oceanic crust. So continents are felsic, meaning they're lighter. They have more quartz. Continental crust, oceanic crust is more mafic, sometimes ultramafic, and in this particular time, most definitely a lot of iron, very heavy. So these float around on this liquid mantle that would be here, and then these would periodically drop. That's what I'm going to go with. So you have the continent, the felsic continent here. You have an island arc here, and this is intermediate rock, which means it's got some of this, and it has some differentiated rock, which means it's got these would be andesites or dacites. These would be rhyolites and granites, and these would be andesites and dacites. Then you have a hot spot like Hawaii, and these are just mafic or ultramafic iron-rich magmas. And then over here, this is representing a greenstone right here, and the greenstones are a whole other topic of discussion. But the gist of it is that greenstone belts are areas of volcanic belts that ended up getting crushed, buried, and metamorphosed. And when you metamorphose a igneous rock, it becomes a greenstone. And that's what this is basically saying right here. So then the greenstones, these end up piling into each other like you see here, and then it repeats. So you'll end up getting series of these, and they're all over the cratons, the nucleuses of continents are made up of a bunch of these, which means that it was a series of arcs that came together to make the continents, and then later on, more stuff started hitting them and making them bigger and bigger and bigger. So this would be the early Earth about 2.5 billion years ago. The moon is much closer in the sky, creating massive tides. I mean, you're looking at tides when the oceans first formed. The tides may have been in the order of hundreds, if not thousands, of feet. Got volcanics going on. I don't know, some sort of shooting star or meteorite there. And these are stromatolites. And this is a representative color. It would have been, well, kind of orange from the gas and the soot. And then I believe the oceans we thought were either basically like a purple. All right, so this is further in the Archean period, 3.8 to 2.5. We are now getting granites, and this line represents the amount of crust, and so 100% is today. We go back in time, we see the majority of the crust was created by the Proterozoic. In fact, 70 to 80% of it. So leads me to believe that plate tectonics is somewhere in here, but we're not sure. So the Archean was a significant change. The continents formed, or the nucleuses of them. Earth had cooled to form a lithosphere, a late heavy bombardment, and we're starting to get rocks. The Archeans where we really start to see some rocks. The Hadean are almost impossible. Very few places survive. The volume of crust accumulated dramatically during the Archean, and 85% of the continental areas were represented. And this indicates, it says here that this indicates that plate tectonics was in action. Well, maybe something was happening because you have all this accretion. And I apologize for doing that. I keep forgetting that. So another thing in the Archean is that, so we're saying that the continents begin to build. Well, what those continents build, they are called cratons. They have continental crust. And again, we show the representation right here. But what's important to know about these is that around 2.5 billion years ago, we start to see a new types of rocks. We see gneiss, greenstones, granites, greywackies, and chert. Chert is really important because it's silica, and it's an ooze that you only find in the deep ocean for a variety of reasons. Okay, you don't find many shallow water sediments prior to this time, so that means there's very little continental margins or passive margins, which means that life was not really given its shot yet. You need passive margins to get life. At least that's the thought. Gneiss is very, very indicative of deep metamorphic rocks being dropped in to the crust in collision zones. So yeah, we're going to say that maybe this is a good argument for plate tectonics, or at least subduction starting. Greenstones, again, metamorphic. They've been brought down. The oceans have the crust has dipped and it's been heated and it's turned into a greenstone. It's not a blue schist, but green. It's different. And this is an indicator that we're not going that deep yet with subduction. Granites, that's differentiated crust. Once you have a granite, your crust has gone through numerous melting cycles, so that's showing mature differentiation. Greywackies are they're just your basic simple rock made of clay, sand, and silt, and it's like a muck on the bottom, and before it starts to change, the first rock it forms is a greywackie. It's a very boring, dull rock. And of course the chert. Craton locations today. All right, so by the end of the Archean, continents had formed, life had colonized the shallow seas, plate tectonics was occurring, asterisk. Atmosphere was gradually accumulating oxygen, although it still has a very long time to go because it'd still be pretty gnarly for us. These are stromatolites. This is Byron Bay. And these are old. I mean, these have been around for a very long time. They are some of the oldest living things. The Proterozoic, 2.5 to 0.54 million, so 541 million. Large plates have developed. Atmosphere has become richer in oxygen, although the content was lower than present day, which is around 20. So we need to form O3, protection from harmful UV rays, and that occurred when we have the oxidation event. You start breaking, you start forming O3. At the end of the eon, 90% of the continents, this is the Proterozoic. By 540, by 1.8 billion years, accretions of volcanic arcs were the primary means during the Proterozoic um, basically what this is saying is that island arcs were now smashing into, we've made our nucleuses of continents, they're kind of roaming around, they're floating on the lithosphere, and then subduction is occurring off to the sides of them because they're moving around and they're slamming into each other, and in order to do that, island arcs form ahead of the actual impact event. So this is Laurentia. This is what we call North America now, and this is the outline of the craton. The Appalachians are right here. They have not formed. They are not part of the craton. You got crust up here, Greenland. This is Baltica. That is what we would refer to as Europe. This is Siberia. That is what we refer to as Russia. You've got, this is China. That might be China, actually. This is Australia. Arabia, this is the Indian Peninsula, the Indian subcontinent, Africa, Amazonia, and then Antarctica you can't see, but it's there. All right, early North America, Laurentia. So outcrops of Precambrian rocks in a broad lowline region represent the shield. Canadian shield it represents several Archean blocks, which means there are Archean crusts that kind of roam around and banged into each other and ended up suturing. A lot of the Precambrian rocks in the U.S. are buried under Phanerozoic strata, and they're just considered. So therefore, because you can see the shield here, the shield is here, but you can't really see it because it's buried under. The glaciers scraped it, pushed a bunch of shit down there, and then the outliers of the craton are deformed from things slamming into them. This over here is a good example of the different cratons that make up the North American shield. I can't see them, but I'm just going to try to. So you got the Ray, you got the Slave Province, Superior, Wyoming. I don't know what that is. I can't read it. This is the Granite Rhyolite Province. This is the Grenville orogeny. So these are all things that were once very, very separate small pieces that slammed in and sutured. This right here is the Trans-Hudson orogeny. That's one of the first continent collisions back about 1.8 to 2 billion years. And this is what the world kind of looked like if you were to look at it. So 2.5 to 0.454, around 1 million years, now we're getting to where we need to be, the supercontinent of Rodinia formed. And this is the last major collision to form. This is the Grenville orogeny. And you see that the Grenville orogeny is right here. Kind of goes down and like that. It's not represented here very good, but this is what the supercontinent looked like. This is 1 billion years ago. You have Amazonia here. You got Laurentia here. This is the east coast of Laurentia. Okay, I apologize. I thought that it had spun around upside down, but I'm wrong. That was ridiculous to say that. This is Argentina right here. So we are actually docked against that. And what's going to happen is these are going to split. This is going to go down, and then this is going to come in. Around 800 to 600 million years ago, Amazonia is here. This is the east coast. This is Australia, Antarctica. They're welded onto the west, basically where the Rockies are right now is where those are. Baltica. But this right here is one of the most important. This connection right here. It is this suture right here that makes the majority of the East Coast that is going to be ready to accept a whole bunch of new real estate when the Iapetus Ocean pulls it. All right, so we know that most of this occurs by plate tectonics. This is just a great simple view. You've got the core. There should be a little circle in here. That would be the iron nickel core that is solid around a liquid outer core. This is a plastic malleable sort of liquid, but it's more like plastic. And this is the majority of our planet. This is basically all the magma, iron rich, This is more iron rich, but it's definitely an iron rich and lower, and then it's sort of um, gets more silicic as you come up. Um, and on top of that, we have oceanic crust floating around, and floating on top of the oceanic crust are the continents. And the continents are being split apart by these ridges. And for instance, continent B is going this way. The question is this forcing it or is this pulling it? And we kind of think it might be both. Just depends where you are. So lithosphere going under, oceanic crust going under. You got scraping stuff from the top of the ocean's crust. You have an island arc form because this is subducting under. It's melting. It's producing magma and volcanoes. So you have an island arc. As this goes down, this is actually being stretched a little bit because this is actually being pulled this way. This is a mid-ocean ridge. This is a dividing center. It's like the Atlantic Ocean. This is just another larger continent here. But this is kind of how it works, and this is going to keep going this way until it smashes into this. And then it's going to build a big mountain range, and then eventually it's going to erode and make these sediments off to the side, and then it's going to melt. It's actually the weight's there's going to be less weight because the sediment's going to go, and then this is going to start to melt again, and it's either going to become this or it could become this. Don't know which. Now this happens. This whole cycle is called the Wilson cycle. So let's just go back, and we're going to start here. The Atlantic Ocean, where we are today. All right, so the Atlantic Ocean is here. This is where we are today. Got Africa, North America. It is eventually going to continue to widen until it gets super wide, probably another third or so of what it is today. And then eventually, one of these sides is going to decide to fail. And it's usually because of sediments on top in conjunction with, when this forms, it's warm, it's buoyant, it's friendly. But by the time it gets over here, let's say off the coast of like Georgia, I mean, that's the oldest crust in the Atlantic. It's cold, it's dense, it wants to go home. And all those sediments that came off of remember the Appalachians are once as high as the Himalayas. So there's a lot of sediment that's been dumped right here. And so what we think is going to happen is that the East Coast is going to start to snap, and it's going to start to subduct again. And I guess if you looked at it looking south, this would make more sense. So in other words, this would be Africa and this would be New England. But this is what's going to happen. This is going to snap and start to subduct. We're going to start getting volcanoes again and island arcs, and then it's going to suck the mid-ocean ridge under, and then we're going to have a whole bunch of stuff happen, which is beyond the scope of this comprehension. But anyway, this will end up slamming it and closing. You'll get this mountain range right here. Eventually, this becomes an unstoppable force hitting an unmovable object, and it reaches a zenith, and then it begins to start to erode. And as it erodes, it starts to get lighter, and all the pressure that was once down here begins to lessen out. This is like a Coke bottle area. You start to take the pressure off, and things start to fizz and bubble and melt. And as they do, they start to separate the two things, and then we're right back where we started again. And a more in-depth version of this is right here. This explains it all. So here we are. This is home. This is today. This is Africa, and that's North America. This is represented by this nice friendly blue circle, meaning there's no volcanic activity, there's no earthquakes. Well, there are, but they're minor. It's basically a tectonically quiet zone. Eventually, one side's going to snap, and then the New England side's going to, New England, Africa. We're going to have volcanoes, island arcs. We're going to have massive earthquakes, and basically the ocean is going to start to shut. And that is represented by this circle here of, this is representing, lava, basic, intrusive, hot magma that's going to be getting jettisoned up as it melts, as the crust subducts, and it will start coming out as volcanoes. Eventually, these two collide, and we get the Himalayas. And the Himalayas, this would be representing them. It's just a big, giant, just no volcanic activity, just giant mountains and erosion. And eventually, like the Himalayas are nothing's really subducting under the other, a little bit. But what's happening is they're just slamming into it. And they're both felsic and they're both light and they're both not going to go anywhere but down and up. And that's exactly what's happening. Eventually, these two things will stop. They'll run out of juice. And now we will start to get erosion. The materials will start to go over here. And this will start to lighten. You'll start to expose the roots, the granite plutons, kind of like Mount Katahdin. This stuff right here, this would be indicative of kind of like what Mount Washington is. This is a trough that got filled. So Washington will be here. One of these will be Mount Katahdin. And also this, if you notice, this has begun to melt and it's begun to thin. Then we come over to stable continent. This is like the Great Plains or the Canadian Shield. And then you go, given enough time, everything thins out, and then you start to get decompressional melting again, and you start to separate, and then you get a spreading center again. And this is basically representing the, that would be the Red Sea. So, anyways, that's that. And I want to make one adjustment.